Welcome back to our course on system engineering. We're continuing to work through this third section, which is focusing on advanced software engineering topics. And so we've talked about software reuse, component-based software engineering, distributed software engineering, and service-oriented software engineering. And for this lecture, we're going to get into this idea of systems engineering. And so the areas that we'll talk about are socio-technical systems, conceptual design, system procurement, system development, and system operation and evolution. So software engineering is not an isolated activity, but it's part of a broader systems engineering process. And we'll get a chance to look at that in this lecture. Software systems are therefore not isolated systems, but are essential components of a broader system that have a human, social, or organizational purpose. So for example, we have the wilderness weather system. It's part of a broader weather recording and forecasting system. And so this is an element that is played in, and we'll talk about systems of systems in the next lecture. These include hardware and software forecasting processes, system users, the organizations. It depends on the weather forecast, etc. So what are types of systems? There's technical computer-based systems. These include hardware and software, but not humans or organizational processes, as well as off-the-shelf application control system, etc. And then there's social technical systems, which include technical systems plus the people who use and maintain these systems and the organizations that own the systems and set policies for their use. And plus there's business systems, command and control systems, etc. For system engineering, this gets into the procuring, the specifying, the designing, implementation, validating, deploying, and maintaining the social technical systems. It's concerns with the services provided by the system, constraints on the construction and operation, and the ways in which it is used to fulfill its purpose or purposes. So let's look at systems and software engineering. Software is now the dominant element of all enterprise systems. Software engineers have to play a more active part in a high-level systems decision making in the system software to be dependable and developed on time and in budget. As a software engineer, it helps if you have a broader awareness of how software interacts with other hardware and software systems and the human, social, and organizational factors that affect the way in which the software is used. So we'll have a couple ways of looking at this, but here is the stage of the system engineering when we're more focused on having a product that's in production and operation. So first of all, you have the procurement, and maybe you're going to have some off-the-shelf components. You have the development, focusing on what exactly you're going to have in a release, and finally the deployment and the operation and having system evolution. So there's a few more things that you need to think about, including some of these initial areas, the conceptual and procurement. So you have conceptual, procurement, development, and operation. So the conceptual design sets out the purpose of the system, why it's needed, and the high-level features that users might expect to see in the system. For procurement or acquisition, the conceptual design is developed so that the decisions about the contract for the system development can be made. In the development, this is where the hardware and software is engineered and operational processes defined. Finally, operation, this is where the system is deployed and used for its intended purpose. So this is a view of that whole process where, including this conceptual piece, that you really have to be thinking with the end in mind and start out first. And so this is where we start to have the requirements, the understanding the concept of what you want to be doing, and coming up with a conceptual way of how it's going to work, and that fits in with everything else. And there's a variety of professional disciplines that are involved in systems engineering. And so here you can see how they're all linked. And so software engineering in this sense is just one of many elements. Various types of engineering, electrical and electronic, a slight difference there. Civil engineering, mechanical, there's ergonomics, user interface design, architectures, as well as software engineering. So since there is interdisciplinary working, there's things that have to be considered. You want to try and minimize communication difficulties. The different disciplines use the same terminology to mean different things. This can lead to misunderstanding about what is to be implemented. You can have differing assumption. Each discipline makes assumptions about what can and can't be done by other disciplines. And finally, professional boundaries. Each discipline tries to protect their professional boundaries and expertise, and this affects the judgment on the system. Okay, let's get into socio-technical systems. These are large-scale systems that do not include software and that do not just include hardware and software, but also people, processes, and organizational policies. Social technical systems are often systems of systems. They're made up of a number of independent systems, and we'll get into that into the next lecture. The boundary of social technical systems are subjective rather than objective. Different people see the systems in different ways. So here's a illustration of the layers of social technical systems. So you have the thing that you're pretty much designing, you're wanting it to be designed to operate in a certain environment, but then there's organizational policies and rules, organizational cultures, organizational strategies and goals, and national laws and regulations that all have to be part of that landscape that you consider. For systems and organizations, social technical systems are used with organizations and are therefore profoundly affected by the organizational environment in which they are used. Failure to take this environment into account when designing the system is likely to lead to user dissatisfaction and system rejection. So here is an illustration of the organizational elements. So you have the systems, and there's people's employment, jobs, there's politics, processes, and policies that all fold into that. So for the process changes, systems may require changes to business processes, so training may be required. There can be significant changes that may be resisted by users. For job changes, systems may reskill users or cause changes into the way they work. The status of the individuals may be affected by a new system. For organizational policies, the proposed system may not be consistent with current organizational policies. For organizational politics, systems may change the political power structure in organizations. Those that control the system have more power, could end up being a result. For complex systems, a system may include software, mechanical, electrical, electronic hardware, and be operated by people. System components are dependent on other system components. The properties and behaviors of system components are intricately intermingled. This can lead to complexity, and complexity is a reason why social technical systems have emergent properties, are non-deterministic, and have subjective success criteria. So in terms of the social technical system characteristics, for the emergent properties, these are properties of the system as a whole that depend on the system components and their relationship. In terms of non-deterministic considerations, they do not always produce the same output when presented with the same input, because the system's behavior is partially dependent on human operators. So that's something you need to think about. In complex relationships with organizational objectives, the extent to which a system supports organizational objectives does not just depend on the system itself. So let's talk about emergent properties. These are properties of the system as a whole, rather than properties that can be derived from the properties of components of a system. Emergent properties are a consequence of the relationships between system components. They can therefore only be assessed and measured once the components have been integrated into a system. So here's an example of some emergent properties. A lot of these are, quote, ility type of things: reliability, repairability, security, usability. So all those are things that you would be assessing as you're seeing it all coming together. And plus there's the volume, which varies depending on how the component assemblies are arranged and connected. So for the types of emergent properties, there's the functional properties and then the non-functional emergent properties. The functional properties, these appear when all the parts of the system work together to achieve some objective. For example, the bicycle has a functional property of being a transportation device once it has been assembled from its components. Non-functional emergent properties, some examples of that are reliability, performance, safety, and security. These relate to the behavior of the system in its operational environment. They're often critical for component-based systems, as failure to achieve some minimal defined level in these properties may make the system unusable. For the reliability as an emergent property, because of the component interdependencies, faults can be propagated through the system. System failures often occur because of unforeseen interrelationships between components. It's practically impossible to anticipate all possible component relationships. Software reliability measures may give a false picture of the overall system reliability. For the influences on reliability, there's hardware reliability, software reliability, and operator reliability that we want to be thinking about. So hardware reliability, what is the probability of hardware components failing and how long does it take to repair the component? For software reliability, how likely is it a software component will produce an incorrect output? Software failure is usually distinct from hardware failure in that software does not wear out. For operator reliability, how likely it is that an operator system will make an error. So failures are not independent and they propagate from one level to another. So here's an illustration of how that could happen. And so you're seeing the hardware, the software, and the operation. So you can have an initial hardware failure that propagates into something of the software. It could cause operations to make a wrong judgment, flows back down to an execution in the software, and then you can have the failure consequences. Maybe that leads to more hardware damage from there. For reliability and system context, system reliability depends on the context where the system is used. A system that is reliable in one environment may be less reliable in a different environment because the physical conditions, for example, the temperature and the mode of operation is different. Thinking about non-deterministic concerns, a deterministic system is one where a given sequence of inputs will always produce the same sequence of outputs. Software systems are deterministic. Systems that include humans are non-deterministic. So a social technical system will not always produce the same sequence of outputs from the same input sequence. For the human elements, people do not always behave in the same way. And system behaviors is unpredictable because of frequent changes in hardware, software, and the data. So in terms of success criteria, complex systems are developed to address, quote, wicked problems where there cannot be a complete specification. Different stakeholders see the problems in different ways, and each has a partial understanding of the issues affecting the system. Consequently, different stakeholders have their own view about whether or not a system is, quote, successful. Success is a judgment and cannot be objectively measured. Success is judged using the effectiveness of the system when deployed rather than judged against the original reason for procurement. What about conflicting views of success? So thinking about the Medcare system, the Medcare system is designed to support multiple conflicting goals, trying to improve quality of care while also trying to provide better information and care costs and so increase revenue. The fundamental conflict is that doctors and nurses have to provide additional information over and above that is required for the clinical purpose. And then they have less time to interact with patients, so the quality of care is reduced. The system, as a result, if you're not careful, the system may not end up being success. However, managers have better reports. The system was a success from a managerial perspective. And you can see different points of view how doing these kind of criteria may end up helping, and others it may actually be causing some more challenges. Well, let's get into conceptual design. In conceptual design, this is where you do an investigation of the feasibility of an idea and develop those ideas to create an overall vision of a system and weeding that down to a particular view and concept. So the conceptual design proceeds and overlaps with requirement engineering. It may involve discussions with users and other stakeholders in the identification of critical requirements. The aim of conceptual design is to create a high-level system description that communicates the system purpose to non-technical decision makers. So here is doing a more focused view in the conceptual design activities. And so you have the concept formulation, and that can take some time. What exactly is it that you want to try and accomplish? You need to understand the problem before you can come up with a solution. And so as you understand that problem, then you come up with the system proposal developments, do feasibility studies for various options, and then have the system structure development. And all of this flows into a system vision document. So for the concept, there's several things related to that. You have the concept formulation, where you refine an initial statement of need and work on the type of system that's most likely to meet the need. Problem understanding, you discuss with the stakeholders how they do their work, what is and isn't important to them, and what they like and don't like about existing systems. In terms of the system proposal development, you set all ideas for possible systems. It could be more than one. Then there's a feasibility study where you compare the systems and assess whether or not the proposed system could be implemented using the current hardware and software technologies. Then there's a system structure development. You develop an outline architecture for the system, identifying where appropriate other systems that may be reused, and then flow this into the system vision document. And this documents the result of the conceptual design in a readable, non-technical way. It should include a short summary and a more detailed appendices. And so user stories, it can be beneficial for presentation of a system vision. And so you can be maybe thinking of like a day in the life. And so I'm not going to go ahead and read this, but here is an example of something that you could be having. Here is another one. And so once again, you see how a certain system could be used by a user. And so you're documenting that out. And so these could be something of benefit in the development process. For system procurement, there is a variety of things that go on. There's the acquiring of a system or perhaps systems to meet some identified organizational needs. Before the procurement, there needs to be several decisions be made of the scope of the system budget, and the high-level system requirements. Based on this information, decisions are made on whether to procure a system, the type of system, and the potential system suppliers. What are the decision drivers? There's things like the state of the organizational system and whether or not they need to be replaced, the need to comply with external regulations, external competition, business reorganization, and available budget. So in terms of procurement and development, it is usually necessary to develop a conceptual design document, high-level requirements before procurement. You'll need a specification to let a contractor for system development, and the specification may allow you to buy a commercial off-the-shelf system, which is can be typically cheaper than developing a system from scratch. Large complex systems usually consist of a mix of off-the-shelf and specially designed components. The procurement processes for these different types of components are usually different. So what are types of systems for off-the-shelf application? They may be used without change, and which needs only minimal configuration for use. For a configurable application, they may have to be modified or adapted for use either by modifying the code or using inbuilt configuration features such as process definition and rules, and custom systems that have to be designed and implemented specifically for use. So there could be a variety of things. And so here are here's an illustration of the system procurement process and for off the shelf. And so you can see that you're basically with your conceptual design, and once you see that You figure out what you want. You can be surveying what are the approved applications that you could select. You select that system and then you place an order. For configurable systems, it's a little bit more complicated. You have a conceptual design, you do a market survey. You can be figuring out if what is the short list of systems that you could use, and then you could be choosing a supplier. It may need that you have to go through this process of refining requirements, and that feeds into the selection for choosing a supplier. Then you get into the negotiation and perhaps modifying requirements. For custom systems, once again, you start with the conceptual design, you define the requirements, you open up a request for proposal, you choose a system supplier, and you negotiate a contract, and perhaps there is some modification of the requirements. Okay, in terms of organization issues, organizations often have an approved and recommended set of applications software that has to be checked by the IT department. And off-the-shelf components do not usually match requirements exactly. So these are some things that have to be considered. When a system is to be built, especially the specifications of requirements is part of the contract for the system being acquired. And for public sector systems, especially, there are detailed rules and regulations that affect the procurement of systems. And then continuing on, for application systems that require change or for custom systems, there is usually a contract negotiation period where the customer and supplier negotiate the terms and conditions for the development of the system. Okay, let's get into procurement decisions. Decisions are made at the procurement stage of the system engineering process are critical for later stages in the process. Procurement decisions often lead to problems such as late delivery and deployment of systems that are unsuited. If the wrong system or the wrong supplier is chosen, then the technical processes of system and software engineering become more complex. So it's easier to figure that out early rather than later. It's cheaper to find concerns earlier rather than later. Okay, well, let's talk about system development. This usually follows a plan-driven approach because of the need for parallel development of different parts of the system. Inevitably involves engineers from different disciplines who must work together. And so this is, we'll show what's called the system engineering V in the next chart here. And so this is how typically you go through the design, and then you do the build, test, and delivery. And so this is the general way, and it is oftentimes displayed this way as a V. So here are the elements. You start with the requirements. This is the requirement engineering is a process defining, analyzing, and documenting the high level and business requirements identified in the conceptual design. The architectural design is where you establish the overall architecture of the system, identify components and their relationships. Requirements partitioning is deciding which subsystems are responsible for implementing the system requirements. Then you get into the moving up and the building, testing, and deployment. So for the subsystem engineering, you develop the software components of the system, configure off the shelf hardware and software, define the operational processes for the system, and redesigning business processes. Then there's the integration where you put the system elements together to create a new system. You do testing. You test the whole system to discover any problems, and then you do deployment. This is the process of making the system available to users, transferring the data from existing systems, and establishing communication with other systems in the environment. For requirements and design, requirements engineering and system design are linked. Constraints posed by the system's environment and other systems limit design choices, so the actual design to be used may be a requirement. Initial design may be necessary to structure the requirements. And as you do design, you learn more about the requirements. So here is the requirements and design spiral that typically happens. And so you start to get more defined with the design over time. With the architectural design, you have review and assessment, figure out any problem and domain and problem issues, do the requirements elicitation and analysis, and have the requirements partitioning, and so on and on. Then you come up with the requirements. So there's various ways of looking at this process, and the spiral is one way. For subsystem engineering, this typically parallel projects are developing the hardware, software, and communications all at once. And so it may involve some application systems procurement, a lack of communication across the implementation teams can be a concern, and there may be bureaucratic and slow mechanism for processing system changes, which means that the development schedule may be extended because of the need for rework. In terms of system integration, this is the process of putting hardware and software and people together to make a system. It should ideally be tackled incrementally so that the subsystems are integrated one at a time. The system is tested as it is integrated. The interface problem between subsystems are usually found at this stage, and there may be problems with uncoordinated deliveries of system components. For system delivery and deployment, after completion, the system has to be installed in the customer's environment. So there's environmental assumptions that, see, there's concerns that might come up, environmental assumptions, human resistance, systems that have to coexist with alternative systems. There may be physical installation problems, data cleanup, and operator training. So all of these have to be looked at. For system operation and evolution, operational processes are the processes involved in using the system for a defined purpose. For new systems, these processes may have to be designed and tested and operators trained in the use of the system. Operational processes should be flexible to allow operators to cope with problems in periods of fluctuating workload. For problems with operation automation, it is likely to increase the technical complexity of the system because it has to be designed to cope with all anticipated failure modes. This increases the cost and time required to build the system. Automated systems are inflexible. People are adaptable and can cope with problems in unexpected situations. This means that you do not have to anticipate everything that could possibly go wrong when you are specifying and designing the system. For system evolution, large systems have a long lifetime. They must evolve to meet changing requirements, and evolution is inherently costly. Existing systems which must be maintained are sometimes called legacy systems. So here's factors that are affecting system lifetime: the investment cost, the loss of experience, and replacement costs. And so all of these are important things that you need to think of. If you've invested a lot of money, you're probably wanting to use it for a long time. But if you start to lose the expertise, that's going to be hard. And if it's a huge replacement cost, that's also something that's going to affect system lifetimes. You're wanting to get a good ROI, a good return on your investment. You want to be watching the risk of changes and what kind of system dependencies that might be there that would affect the system. In terms of cost factors and system evolution, proposed changes have to be analyzed very carefully from a business and technical perspective. Subsystems are never completely independent, so changes to a subsystem may have side effects that adversely affect other subsystems. And reasons for original design decisions are often unrecorded. Those responses for this system evolution have to work out with why these decisions were made. As systems age, their structure becomes corrupted by change, so the cost of making further changes increases. So we'll just finish up with a couple charts, several charts with key points. System engineering is concerned with all aspects of specifying, buying, designing, and testing complex socio-technical systems. Socio-technical systems include computer hardware, software, and people, and are situated within an organization. They are designed to support organization or business goals and objectives. The emergent properties of a system are characteristic of the system as a whole rather than as a component part. They include properties such as performance, reliability, usability, safety, and security. The fundamental system engineering process are conceptual systems design, system procurement, system development, and system operation. Conceptual system design is a key activity where high-level requirements and a vision of the operating system is developed. System procurement covers all of the activities involved in deciding what system to buy and who should supply the system. Different procurement processes are used for off-the-shelf application systems, configurable COT systems, and custom systems. System development process include requirement specification, design, construction, integration, and testing. When a system is put into use, the operational processes and the system itself inevitably change to reflect changes to the business requirements in the system's environment. Okay, well, thank you very much. That will be finished this lecture.